It's hard to explain the engineering marvel that is the SR-71 Blackbird, a long-range plane capable of flying 26 kilometers above the surface of the planet, so high that the pilots could see the curvature of the planet and the inky black of space from their cockpits. It flew so fast that the engineers had to develop entirely new materials and designs to mitigate and dissipate the heat generated from aerodynamic friction. Entirely unique engines were needed to function from 0 all the way up to Mach 3.2, dealing with the myriad of problems like cooling, fuel efficiency, and supersonic shockwaves interfering with airflow. A plane so advanced that when it detected a surface-to-air missile, its response was simply to change course and speed up. Even though the missiles had a higher top speed, they couldn't achieve the range and high-altitude maneuverability the Blackbird could. This allowed the SR-71 to run hundreds of missions through Vietnam, North Korea, and Iraq without ever losing an aircraft to enemy fire, despite multiple attempts. The entire plane was built around the propulsion system, which alone was a miracle of engineering design. For one, no turbine-driven jet engine can operate with supersonic flow at its inlet. Yet, this plane was powered by the Pratt & Whitney J58 turbojet engine. But get this, off the shelf, these engines could only provide 17.6% of the thrust required for Mach 3.2 flight, a speed which the SR-71 could cruise at for extended periods of time. How on earth did it manage that? In order to achieve those kinds of speeds, a ramjet is typically needed. No moving parts, this type of engine is capable of flying at speeds far greater than a typical turbine-driven engine. But it cannot start from 0. It needs forward movement in order to achieve the correct compression of air in the combustion chamber. So, they are either dropped from a conventional plane, have a secondary propulsion system, or are a hybrid of a conventional jet engine and a ramjet, which is precisely what the SR-71 used. Ducts were the primary mechanism that transformed the engine from a turbojet into a ramjet. Afterburners are great. They significantly add to thrust without needing a whole lot of additional weight. They basically just inject fuel into the exhaust of the jet engine and ignite it with whatever oxygen is left to provide additional expansion and therefore thrust, but they are really inefficient. However, as the speed increases, they are the only feasible way to generate thrust, and they do gain efficiency thanks to the forward motion providing the compression of air needed to run them, instead of the turbine needing to be powered to turn the compressor stage. The crazy thing about the SR-71 is that the engineers could have eked out more thrust from this engine to increase the top speed even more. Ramjets can go up to Mach 5, so why did they stop at 3.2? Would they have run out of fuel? Fuel efficiency in terms of cost doesn't mean a whole lot to a military plane like this. The military doesn't care about cost, but the more fuel you carry, the heavier and bigger the plane gets, increasing the fuel it uses. There is a break-even point and the plane's range will be limited. But the engineers did manage to fill the plane up with an astounding amount of fuel with some clever engineering. The plane was strictly a surveillance plane, so no internal volume was used for weapons, freeing up space for fuel. You have probably heard that the SR-71 leaks fuel on the runway because there were gaps in the fuselage, but that's a simple fact that ignores much of the engineering that caused it. The SR-71 used something called a total wet wing fuel tank system, which meant that the fuel was not contained within a separate fuel bladder. This was a weight-saving measure. Separate metal fuel tanks would add too much weight, and lighter plastic ones would melt from the intense heat generated from the aerodynamic friction. So, the fuel was contained by the skin of the plane itself. The engineers applied sealant to every gap the fuel could possibly come out of, but because the titanium skin of the plane expanded and contracted with every flight, it gradually deteriorated over time, allowing the fuel to leak out. Because of this, the SR-71 had to regularly go into maintenance and have sealant reapplied, but it usually came back still leaking, just not quite as much. The number of man-hours required to reduce it to zero was simply too great to fit it between flights. Even then, without the ability to refuel in the air, this plane would have had terrible range for what was supposed to be a long-range spy plane. Range varied greatly. For example, the engines became significantly less efficient when the outside temperature was higher. A fully loaded SR-71 could expect to burn nearly 13 metric tons of fuel, accelerating from Mach 1.25 at 30,000 feet to Mach 3 at 70,000 feet, if the outside temperature was 10 degrees Celsius above standard. That is 36% of its fuel capacity. If it was 10 degrees below standard, the fuel burn nearly halved to 7.2 tons. And of course, the range was severely affected by their speed and use of the afterburner. But on average, the SR-71 had a range of about 5,200 kilometers, about enough for a one-way trip from New York to London. Not terribly useful. The US was not going to be landing at their target to hand over a top-secret plane to the enemy. However, with aerial refueling, the plane could stay in the air more or less indefinitely, provided there was no mechanical issues. Really, the range was entirely determined by the pilots. The longest operational sortie occurred in 1987 when the US flew the SR-71 from Okinawa to observe developments in the Iran-Iraq War. This mission lasted 11.2 hours and likely required at least 5 aerial refuelings along the way. So, if it wasn't the fuel or engines that limited the SR-71's top speed, what did? Fuel needed to be specially formulated to get around these overheating issues. It was a specially formulated fuel called JP7, which has very low volatility and a high flash point. This was partially needed because the fuel leaked on the runway, and they needed a fuel that wouldn't ignite or easily evaporate and make the ground crew ill. But mostly, they needed a fuel that wouldn't vaporize in the tanks and cause fuel feed and pressurization problems. The JP7 fuel was so stable that it actually doubled as a coolant for the entire plane. The fuel was pumped around the airframe to cool critical components like the engine oil, hydraulic systems, and control electronics. When the fuel got too hot, it was simply sent to the engines for combustion. The fuel was so stable that the plane actually needed to carry shots of triethylborane, a fuel that spontaneously ignites in the presence of oxygen, to start the combustion cycle and afterburners. The plane usually only carried about 16 shots of this, so the pilots needed to manage them carefully, particularly when slowing down for refueling and managing unstarts. One huge question I had about the SR-71 was why it was painted black. Airliners are all white to reflect heat and prevent the plane from overheating. If that applies to an airliner, why not the SR-71? The SR-71's predecessors were unpainted, which saved weight, and the areas exposed to highest temperatures were painted black. Why was this? Surely black would absorb more heat. The Concorde was once painted blue for a Pepsi ad campaign and had to lower its speed as it absorbed too much heat from the sun. However, the Concorde did not fly nearly as high or as fast as the SR-71, and as the SR-71 rose, the energy it absorbed from the sun dwindled in comparison to the heat it gained from aerodynamic friction. For this, we have to refer to something called Kirchhoff's rule of radiation, which tells us that a good heat absorber, like a black object, is also an equally effective heat emitter. So, the black paint helped the SR-71 radiate heat away from the plane, as it allowed the plane to radiate more heat than it gained from the radiation from the sun. These efforts helped to keep the plane cool, but the structure of the plane still needed to be incredibly heat stable. Aluminium is typically the material aircraft engineers turn to. It was used for the Concorde, but as we saw, it too had its speed limited by heat to a much lower Mach 2 within its crystal lattice that resist heat from breaking them apart. Titanium alloys can resist temperatures up to 600 degrees Celsius before their atoms begin to diffuse and slide over each other significantly, allowing it to retain much of its strength even at 300 degrees. It has also very low thermal expansion, so that expansion and contraction we mentioned earlier is minimized, reducing the thermal stresses in the aircraft. But titanium has its limits, and for the SR-71, this was about 3.2 Mach. Today, engineers have made huge strides in material science. The SR-71 used heat-resistant composite materials as radar-absorbing wedges between the structural frame, located in these locations. The manufacturing techniques needed to make composite materials as load-bearing structures did not yet exist, but that has changed.